Swayam Prabha. Digital India. Educated India.
On extreme scale computing. Like we have already talked about how India kind of lags behind in, top supercomputing efforts and all. So if you have any questions, like during the talk, of course you can ask him, but if there are some detailed discussions you want to do with him, he has to step out for some time, but he'll be back at 4:30 again.
Yeah.
Okay?
Okay. Thank you very much, Professor Preeti. I'm Aditya. I recently joined IISc as an assistant professor. I'm in this new department called Department for Computational and Data Sciences. So yeah, before I start, I would like to acknowledge Preeti and Ashish for giving this invitation and hosting this event. And I would also like to acknowledge my collaborators in the work that I'll be showing, Diego Donzes, Thorsten Hofler, Hemant Kolla, and Jacqueline Chen. So before I move to the talk and give you the outline, I would like to quickly talk about this new department, Department of Computational and Data Sciences at IISc. So the CDS department has been started under the Interdisciplinary Research Division at IISc. So IISc previously had this supercomputing center, which had both the supercomputer facility as well as the academic part of the computational science. So recently in 2015, a new department was carved out, taking the academic part of the SERC. And I'm Aditya. I recently joined IISc as an assistant professor. I'm in this new department called Department for Computational and Data Sciences. So yeah, before I start, I would like to acknowledge Preeti and Ashish for giving this invitation and hosting this event. And I would also like to acknowledge my collaborators in the work that I'll be showing, Diego Donzes, Thorsten Hofler, Hemant Kolla, and Jacqueline Chen. So before I move to the talk and give you the outline, I would like to quickly talk about this new department, Department of Computational and Data Sciences at IISc. So the CDS department has been started under the Interdisciplinary Research Division at IISc. So IISc previously had this supercomputing center, which had both the supercomputer facility as well as the academic part of the computational science. So recently in 2015, a new department was carved out, taking the academic part of the SERC and rebranded into computational and data sciences. So we have a lot of interdisciplinary research faculty coming from computer science, mathematics, physics, biology, mechanical engineering, chemical engineering, from different areas of work. And we are currently under the Faculty of Engineering at IISc. So our department offers three postgraduate programs. The first one is a PhD program in engineering. The second one is MTech research program, where you have to do a thesis after doing the coursework. And then after that, you have a MTech coursework program, where the focus is on doing coursework on computational and data sciences. We have about 16 faculty, and we get major funding from MHRD, DST, and a lot of funding from private sources as well, Microsoft Research, IBM, Google, Yahoo, Boeing, etc. Applications, how do you bridge both? So you need some sort of a method or algorithm development that comes under the focus area of methods. So these are the topics of active research that are currently happening in CDS. We have CAD design for VLSI. There are several labs working on grid applications, distributed computing, machine learning, database systems, video analytics, and computer vision. All these things come under the computer and data systems part of the CDS. The other part is the computational science part, where we look at computational electromagnetics, computational photonics, medical imaging, scientific computing, and mathematical libraries like the linear solution libraries. We also extensively work on computational fluid dynamics, computational biology and bioinformatics, and also looking at numerical linear algebra. So with this, I would like to start the talk by providing a brief outline. So I'll start with some brief introduction about scientific computing, and mainly in the context of how you can model different systems using partial differential equations and how you go about solving those on large HPC machines. Second, I'll talk about some introduction on PDE solvers. then talk about the new asynchronous computing method that I've been working on. I'll talk about its implementation using MPI model, and then show you some performance results. Towards the end, I'll show you some research highlights that I'm working on currently, and then finally provide you some conclusions. So here, if you consider scientific computing, this is used in several different areas. So the first picture that you see is a highly resolved simulation of a turbulent flow in its simplest form, which is called the homogeneous isotropic turbulence. As you see, this is a computer-generated image. So we solve set of partial differential equations and then obtain the results from the equations and then plot those to look at flow fields like this. Scientific computing is also used in weather prediction, climate modeling, and also used in doing detailed simulations of combustion simulations, reactor simulations, biology, and so on. The typical workflow that we follow is we have a set of governing partial differential equations. These equations are discretized or approximated using different kinds of numerical methods. And once you have once you apply the numerical method, the differential equations become algebraic equations. Now, these algebraic equations have addition, subtraction, multiplication, and division, which are easily understood by the computer, which can be programmed on a computer. And then, so the programming part is done, and then we perform simulations. So once we do simulations, we get a lot of data, and we analyze the data to understand the physics behind all these phenomena. So try to get some analysis done, try to understand some phenomenology, and do some science discoveries. So recently, we have two big rapid changes happening in computing technology. The first one I would say is in terms of HPC or high performance computing. The second one is in terms of ML and AI. And so here are some of the top supercomputers in India. So the first one is at IIT, and this is from Indian Institute of Tropical Meteorology, Pune. So with the availability of HPC or supercomputers, what we have is availability of petaflops or towards exaflop machines. So with this, what we can do is instead of doing simple, smaller calculations, we can go to really big and detailed calculations. So we increase the grid resolution at the current state of the art to the order of a billion grid points. So I'll tell you what these grid points and other things mean in a couple of minutes. So once you have this HPC machine, you are able to solve these big simulations. So once you have a lot of data points, what will you have? You'll have a lot of data to analyze the whole simulation process. So the data is currently of the order of tera or petabytes, depending on the kind of scale at which we run. And then once we have this large data, it cannot be loaded on a single desktop or a single workstation to analyze it. So you need to analyze the things in a distributed way. In addition to that, it's very difficult for one person or one research group to analyze the data in its entirety. So what we are currently looking at is to use ML and AI methods to come up with automated analysis for at least the preliminary stage so that the experts can look at more detailed aspects of the data by reducing the data. So in this context, we are looking at detecting patterns in the data. So these are essentially useful in identifying the structures in the flow, as you see here. And then we can also create models for reduced order modeling. So you can do one detailed calculation and create a machine learning model from the detailed calculation. And then what you can do is you can do small scale industry relevant problems on smaller workstations or so. So this is in the context of subgrid modeling and reduced order models. So once we have the ML and AI algorithms, we want to do these things in a distributed setting. So we also have to work on distributed analysis algorithms as well. So this is the overall context of scientific computing that we are currently interested in. So now I'll start with a simple example of a fluid dynamics example. So this is a turbulent flow. So a turbulent flow can be thought of as, so you open a tap, initially the water comes very smoothly, right? And once you increase the flow rate, you open the tap further, it becomes very noisy. So that kind of state of flow is called a turbulent flow. And a turbulent flow is characterized by multiple scales. By scales, I mean that, so you see a very bright patch here, brighter yellow, and inside that there are smaller and smaller structures. So this is what a multi-scale phenomena is. So for example, you look at a cloud in the atmosphere, you see that there is a huge cloud, and within that huge cloud there are smaller and smaller structures. So these are the resulting phenomena and characterized by the multi-scale nature of the problem. So when we do direct numerical simulations, try to simulate these flows with complete resolution of dynamic scales, what we have are a set of large scales characterized by a length scale L. By length scale, I mean, so in this context, you can consider L to be the size of the cloud, and then the smallest scale called the Kolmogorov scale, which is the smallest structure within the cloud, that is characterized by the value eta. So if you could do some theoretical analysis, you can arrive at the scale separation or the ratio of the scales as L over L, and these scales as something called a Reynolds number, which is a non-dimensional number that characterizes the multi-scale nature of the flow, and then the exponent is 3 power 4. Okay. So, and in terms of practical applications, it is very large. That means the scale separation is really large, which means that you need a very fine grid to resolve the physics, which means that you need to do a lot of computing and you want to use HPC. And how does the computational effort goes as we increase the Reynolds number? For example, if I double the Reynolds number, according to the relation that we have obtained from the theoretical analysis, the computational effort goes by 8 times. And you can imagine that currently we are able to simulate using direct numerical simulation. The biggest Reynolds number that we can simulate in terms of Taylor microscale is around 1000, and the practical flows occur at 10,000. And I will show in the next slide that if you use the traditional approaches, it will take about 50 more years to reach the practical value in terms of simulations. So the idea here is that we want to use parallel computing as much as possible to scale up the problem, and this talk will be about how to do that efficiently. So I take the same problem, the homogeneous isotropic turbulence. It's a direct numerical simulation which uses a pseudospectral method. This is a way of approximating the differential equations. I'll get to this in a minute. And once you have a simulation like this, we want to see how these simulations have evolved over different years. And this is a function of the availability of the computing power. So for that, I have given a graph here. So on the x-axis, we have the increasing number of years, starting from 1940s to the latest, 2019. On the left y-axis, we have the operations per second or flops. On the y-axis, we have the Reynolds number that has been computed at a particular simulation and in a given year. So as you see here, as you start from 1940s to the current, the computational power has increased exponentially. So this is in a log-log scale, so the increase is exponential. And similarly, if you see, there has also been an exponential increase in the kind of quality of simulation that we can do. You can see that earlier in 1970s, we were able to simulate about a Reynolds number of 5. Now we are able to simulate a Reynolds number about 1000. And if you extrapolate, we want to go to 10,000. This goes beyond this graph, maybe in 2050. All right. One thing that I want to mention here is that if you consider the first dot, this is the first simulation in 1970s, and the last dot here, the numerical method has been the same. What has changed in the code is the way you achieve the parallelism, or the way you achieve the increase in the computational rates. So that's what has changed. Nothing has changed in terms of the numerical method. So I'll take a different example. This is also what I'm working on currently. This is relevant to turbulent combustion. So turbulent combustion is common in all your IC engines, in your vehicles, aircrafts, and so on. And what was achieved in one of our first simulations, this is a simulation done using the code S3D. This is one of the exascale computing codes in the US. We were able to do a very small 2D problem with a single step chemistry. That means if you consider hydrogen, you want to burn hydrogen using air, you have H2 plus O2 gives H2O. Of course, this is not stoichiometrically correct, but you have to have appropriate coefficient. So we were using single step chemistry in this particular case. And this was a study problem. By study problem, I mean that we do not capture the dynamics in the flow. We just capture the average behavior. As you move further to the point 2 here, we were able to get to unsteadiness in the flow. So we were able to capture the transient events like ignition, flame propagation, and so on. And then as we move further up, we were able to go from 2D to 3D simulations, and now we are able to use detailed chemistry. By detailed chemistry, I mean that when you have the same example of hydrogen and air, so usually it is H2 plus O2 gives H2O. That is a single step chemistry. But in practice, it doesn't happen that way. What happens is first an H2 molecule will collide with an O2 molecule, forming some OH and H atom and so on. So usually the formation of water from hydrogen and oxygen takes up about 9 to 10 species, and the number of reactions is of the order of 20. So we were able to get to that level of detail of calculation as we have increased computing time. And then now we increased further from 20 species to about 100 species. So these are species that represent something like a diesel fuel or petroleum fuel. So that means the more higher hydrocarbon it is, you need more species to represent the chemistry, and the more detailed calculations or the computing effort increases to compute those. And further, now we are able to do, so if you see here, all of these things are in a box or a cuboidal domain. But now we are able to do DNS of complex geometries that are relevant to industry now. So this is a multi-block geometry that we have recently developed into this code S3D, and we are able to scale up these simulations up to about 200,000 processors or 2 lakh processors. So with that brief introduction, I would like to talk about how we solve these equations with a simple 1D example. So before that, so I've shown you some examples from turbulent combustion, right? These are the set of equations that we solve for getting the solution. So the first one is the conservation of mass equation. The second one is conservation of momentum. Then we solve for conservation of energy. And you have different species associated in the chemistry. So these are all the equations for conservation of species. All these are tightly coupled partial differential equations with strong nonlinearity arising from these advection terms, and this makes it very computationally challenging and results in a multi-scale nature of the problem. So what you do is, once you have these PDEs, these PDEs cannot be directly programmed onto a computer, right? It has to be algebraic operations. So what we do is we use different kinds of discretization methods. So there are several examples of those. There is finite difference, which is what I will be focusing on this talk. You also have finite volume, finite elements, spectral elements, pseudospectral. So the procedure is that when you do these simulations, you take the governing set equations and then approximate these equations using any of these discretization methods. Once you have the discrete PDEs, which are mainly algebraic equations, you discretize the computational domain into really small parts or really small elements, and then you use your initial and boundary conditions, develop an algorithm, use that algorithm to do the simulation. So I'll take a simple 1D example. Yes?
So what's the relation between Reynolds number,
Right.
increasing difficulty, and these PDEs?
I mean, you mean in terms of computational effort?
Yeah, in terms of computation.
Yeah, so that was there in the earlier slide. So the relation is the computational effort goes as Reynolds number power 3. So that means if you double your Reynolds number, your computational effort goes by 8 times. Any other questions? Okay, so I'll take a simple 1D example here. And so what you have is a simple unsteady heat equation. So this can be considered as a rod. I have a burner here. I put a matchstick or something below this rod. So what that does is it increases the temperature locally at this point 0, and eventually, as if you give sufficient amount of time, that heat starts, conduction process starts, and then the heat diffuses in this direction, right? So we want to simulate this particular problem using finite difference, and then with this example, I'll also show how to parallelize the code. So these class of problems are often referred to as stencil-based computations in the HPC community, mainly because, so I'll get to that in a minute. So what you do is you have this PDE, you have this computational domain. I fragment this computational domain into smaller chunks, like these are the grid points of the domain, and each grid point has a specific ID, and the generic ID is I. So the function u, or the temperature, is varies both in terms of space as well as time. When you have a discrete domain, I know where I am computing the solution. So the x becomes xi, where xi are all the grid points on the 1D domain. And we also do a time marching. So you start from some initial condition, which is at t equal to 0, and slowly start marching to delta t, 2 delta t, 3 delta t, and so on. So those are the time steps Tn. So now whatever we compute is mainly in discrete form at a grid point I and at a time level n. So first we take the time derivative. It can be approximated using a very simple scheme, which is the first order accurate forward difference. So in this scheme, if you are using some initial condition and doing a time marching, the only unknown in this equation is the value of the function or the temperature at a particular grid point I at the advanced time, which is n plus 1. This is the approximation, and then the error associated with this approximation is of the order delta t. By order delta t, I mean that if you refine your delta t, so if you reduce your delta t, the error goes linearly with increasing the grid temporal resolution. Similarly, I also want to approximate the spatial derivative. So I can do it in two different ways using a second order accurate central difference. The first one is called explicit in time. So by explicit in time means, so I can approximate these derivatives at two different time levels. I have two time levels in my time derivative. One is at n plus 1, the other is at n. I can evaluate my spatial derivative either at n or at n plus 1. In the first case, I choose to evaluate my spatial derivative using the function values at time level n. So this results in an explicit formulation that is given here. Here in this case, the error goes as delta x square, which is second order accurate. That means if you increase the grid resolution, so if you increase the grid resolution 2 times, the error drops by 4 times. I can also evaluate the same derivative using implicit scheme, where you evaluate the spatial derivative at time n plus 1. In this particular case, all these function values are unknown. So when you have implicit discretization, you will end up with a linear system where you can use commonly available linear solvers to perform the simulation. So for this particular talk, I'll just consider the explicit time discretization. Okay. So if I plug in these two, second one, what I end up is an algebraic equation that is shown in this top. So this can be written in a vector form as u at n plus 1, which is a velocity vector at different grid points, the function u at the previous time level, which is n. So now this can be simply programmed using two different for loops. Yes.
This explicit method one is stable?
It is stable if your CFL condition is less than or equal to 0.5. Right? The implicit scheme is unconditionally stable. I have gone with explicit because we are interested in exploring the HPC aspects, and it is easier to explain it this way. So I will quickly summarize the computing with respect to a pseudocode. So what we have is we have a set of grid points where we have an initial condition for the temperature. We want to see how the temperature evolves in the space, and for that we need to have the first one is a outer time loop to evolve the solution in time, and then to compute the solution at each grid point we have a second for loop which is indexed with I, which goes from 0 to the total number of grid points. And this equation can be rearranged to get the u at n plus 1 is equal to some coefficient times the vector values at the previous time level. So is this clear? Is the pseudocode clear? So once we have this, we just evolve this until the end time that we are interested in, and that's the solution at the end time. So now you have the temperature values at some evolved time, which is what we are interested in. So this is a very simple example, and we can come up with more complex examples relevant to combustion or any of the other simulations. So just quickly, so you have asked about the stability condition, which comes under the numerical properties. So the numerical properties we want to analyze mainly in terms of the stability of the solution. That means that if I evolve the solution in time, will my solution be stable? By stable, I mean that will the errors decrease or remain constant, or are the errors going to increase? If the errors are going to increase, I'll end up with an incorrect or inaccurate solution. The second one is consistency. By consistency, I mean that do the approximations of the PDE, which are algebraic in nature, if we refine the grid sufficiently smaller, like if the delta x and delta t tend to 0, am I recovering my partial differential equation or not? If not, it is an inconsistent system. The third one is accuracy. How accurate are my solutions with respect to the delta t and delta x I have chosen? So, to analyze all these three properties, the normal parameters for the traditional or the textbook way of computing are the grid resolution, which is delta t and n, and the nature of the partial differential equation. It can be hyperbolic, parabolic, or elliptic, and the kind of parameters that are embedded in the equations, like the Reynolds number, the one that comes from the stability, which is the CFL number, and etc. Okay. So once we have understand the numerical properties, we want to get into the parallel implementation. Here we choose a implementation based on data parallelism. By that we mean we want to decompose the domain into several subdomains and distribute these subdomains to different processing elements where we come up with a parallel algorithm. So I come back to the same equation. We have the ui at n plus 1, which is unknown. We want to compute this algebraic equation at different grid points. If I take a generic grid point I have to compute the spatial derivative, where the solution depends on I and I plus 1 and I minus 1, right? So with respect to the stencil operations, this is a 3-point stencil, and this can be trivially computed on a single core machine or single processing element, because all the values of the functions at different grid points reside in the same memory, and in that particular case you do not have network communication and so on, so the programming becomes very easy. We want to do the same thing in parallel. So now what happens if I want to compute the spatial derivative at this point I? So in this particular case, first we divide the domain into two subdomains. Let's say I have two processing elements available to distribute the computing. I divide the domain into half. So these are the two halves. Now I want to compute the spatial derivative at the same point I. So now I is here. I want to compute I minus 1, which uses I minus 1. The I minus 1 is actually being computed in the neighboring processing element, right? So what we do is to make a copy of this here. This is mainly to enable the computation of this spatial derivative. We divide the whole set of grid points into 4 different classes. First ones are the physical, the black points, which are the physical interior points. So these are the points where the computations are independent of the communication that is associated with the problem. The second ones are the physical boundary points, where you apply some particular boundary condition. So these are usually at the ends of the domain. And the third one is a processing element boundary point. By this I mean these two gray points, where in order to compute this particular algebraic equation, I need the value from my neighboring processor. To facilitate that, we use a buffer, or we make a copy of this on this particular processor. So that is the ghost point or a buffer point, and we make a copy through communication. So the communication typically happens in 2 steps. One is you start the communication process, and then to ensure that the communication is finished, we do some kind of synchronization. So I'll talk about this in a minute. So as you see, that these are all point-to-point communications. So you have done this advanced MPI course 2 days back, where they have explained about MPI gather, broadcast, and other things. So all those are collective communications. In this particular case, we do not need a collective communication. What we need is a point-to-point communication. I just need to communicate with the neighboring processing element where we share this ghost or the buffer point. That's all. So for this, there are, as an example, I show 2 different examples. One is I can use MPI send and MPI receive. So this processor, which has to receive the value, will post an MPI receive at this end, and the source processor, which is a PE0, will post an MPI send. So the send will start the communication, and then the receive receives it in this particular buffer. And once that communication is finished, we proceed with the computations. The same thing can be, and here the computation happens both ways. We can also use MPI send receive in this particular context. So a simple time loop would involve 2 different things. The first one is to perform the communication of data, And once we perform the communication, we have all the values at the current time level. Once you have that, you compute the solution at all the points and evolve the solution from n to n plus 1. And this is the workload in a particular, for a given time loop. So one thing that I want to point out is that these kind of point-to-point communications are blocking communications. By blocking, I mean that when you issue these function calls, the other aspects of the code which are associated with computing are not performed. So the code will proceed further only after the communication is finished. So these are referred to as blocking communications. And with this, what happens is that when you issue a MPI send receive, it's just send and receive. So during the process, while the communication is happening, the CPUs would typically remain idle. And this would affect what is called the scalability of the code or the performance of the code. So with respect to these two point-to-point communication calls, these are blocking in nature and we cannot achieve a computation-communication overlap. So to get rid of that particular issue, MPI also has what is called a non-blocking communication pattern. For this, the communication happens in two steps. First, the source processor would issue an MPI ISEND. The receiver processor will issue an MPI IReceive. And once these two are issued, the communication process starts. And while this communication is happening, now you can start computing other things that you want to do. So in that particular case, you do the other computations and then finally post a wait, which will do the synchronization of the communication and ensure that the values in the buffer are updated. And then you can compute the values that are in the gray color. So as a simple example, first what we can do is we can start the communication at these buffer points. Once you start the communication, you can start the computations at all of these black points where the computations are independent of communication. That means they do not depend on the values that you are receiving from the neighboring processor. So in that particular case, you achieve a computation-communication overlap. So once you have the computations done at these points, now you come back to your communication. You post an MPI wait to check whether the communication is finished or not. If it is finished, it will proceed further. If it is not finished, it will wait and ensure that the communication has been synchronized. Once that is done, you can do the computations at these gray points and proceed to the next time step. By this, what we are achieving is a computation-communication overlap, which will help us in improving the scalability of the codes. So this is done at an MPI level. So you have asynchronous communications that are enabled to increase the scalability. So in terms of asynchronous communications, in addition to MPI ISEND, IReceive, you also have one-sided communications. So MPI ISEND and IReceive are two-sided communications, which means both the source processor and the destination processors are involved in the communication process. MPI also supports one-sided communications. In this particular case, either the source, either one of the source or the destination are involved in the communication. So if the source is involved, you have MPI put. What you do in this particular case is that wherever you want to send the value, you expose that as a remote memory for the source processor. And the source processor will go put the value into the remote memory and come back. And similarly, you can also do it at the target level where you post a MPI get. This will go and take the remote value from the source and put the value into its own buffer and then do the computation. So these are the different communication algorithms available in terms of MPI standard. Any questions on this? Do you want me to do an illustration using a simple picture? So let's say I have two different processing elements. So this is P0 and P1. I want to put this value from here to here. So what I do is I take this whole memory piece and I want to put a value here. So I will expose this as a remote memory for the processor 1. So for processor 1, I'll initially expose, so there is something called creation of a window. A window is nothing but a remote memory. So I use MPI win to expose this memory as a remote memory to this processor P1. So once P1 knows that this is my the location of the remote memory, when I use an MPI put, it will take this value and put it here and then finishes the communication. So there are different kinds of synchronization calls that are available with this one-side communication. I'll not get into those details. I'll be happy to answer those after the talk. Okay. So now that we have a brief introduction about finite differences and how to parallelize them, I'll now talk about the asynchronous computing method. Oh, okay. So before that, I want to quickly talk about the scalability. So now we have seen how to do the implementation in parallel, right? So now how do we evaluate the scalability of the code? So suppose if I take a particular problem and it takes t amount of time to compute the solution, I can use two different processors and split the domain into two. And now what you can do is, in principle, what is the computing time? It will be t over 2, right? However, you also have, in addition to computing time, you also have communication time. That adds some overhead. This overhead is C2. So the total simulation time now is equal to t over 2 plus C2. And you increase the number of processors to 4, you will have 4 different subdomains, and you have the communication associated with all the 4 nearest neighbors, and then you have the total computing time to be t over 4 plus C4. So we can get a theoretical scaling of how the ideal scalability is. What we are interested in is in computing the solution. So we are not worried about or we are not considering the communication time. If we just consider the computing time should decrease with increase in the number of processors, and this is a linear scalability relation. However, you also have communication overheads. So what will that do to your code? So for that, I show you a simple example called the strong scaling graph. What I do is I take a particular problem like this. I increase the number of processors and see how much time is it taking to compute one time step in my solution. Right? This is a metric for the benchmarking of the code. So initially, we are at of 1024 processors, and in this particular case, we have some X amount of time. Ideally, the time should become half, which is depicted by this dashed line. However, what we measure is a point that deviates from the ideal scaling line. And this deviation is because of the communication time. If you increase it further, you see that the gap widens with respect to the ideal scaling line. And these are mainly because of the communication overheads. And currently here we are at of the order of 10,000 processors. As we move towards exascale, we will be using about million processing elements. And all these million processing elements, if you have heard earlier talk on interconnect and network communication, will be connected by complex network topology. And with this million processing elements, you will have increase in the number of communications. And this will affect the scalability, right? In addition to this, you will also have what is called performance variability. So when you have a supercomputer, it occupies a large floor space. You will have different racks, and these racks are cooled to maintain low temperature of these computing chips. And sometimes what happens is the cooling may be inadequate in one particular processor. So what the operating system will do is, it will reduce the clock speed of that particular locally, so that it reduces the heat that is dissipated. So that means you are now one of the processors is computing at a lower speed. Now my mathematics ensures that there is synchronization across different processing elements. So what will that do? It will, so if one processor is slowing down, all the others will slow down because of the communication dependency, right? So performance variability across processors or processing elements will affect the scalability as well. Also, there are synchronizations that are enforced at different levels. As you have seen earlier, there is synchronization because of the communication, and that mainly appears because there is synchronization at a mathematical level. And then there are synchronization at different other levels that we are not going to discuss here. In addition to these things, there are something called system faults. When you have a machine with millions of processing elements, it is always possible or probable that one of the processing element fails. What will happen to the simulation then? If one processing element fails, That means my solution at one fraction of the domain is not being computed. If I don't get the solution there, I cannot evolve the solution in the other processing elements. That means the whole simulation goes waste. So you need to address system faults as well. So these are some of the key challenges as we move towards the next generation of supercomputing, which is an exascale computing machine. And this machine would perform 1 exaflop of double precision computations. Okay. So what are the solutions to resolve these issues? What are the parameters for that? The first one is we want to minimize the data movement to increase the scalability. The second one is we want to move away from bulk synchronous programming models or programming models where you need a lot of synchronization of data. The third thing is we want to express data locality and data independence. This again, this will result in data minimization, okay? Data movement minimization. So in terms of research, people are looking at a software level, people are looking at asynchronous runtime systems. And in terms of communication models like MPI, people are looking at asynchronous communications. And what we are interested in our group is mainly in terms of at a mathematical level. What we want to develop are asynchronous numerical methods that would relax the synchronization necessity at a mathematical level. If I relax the synchronization necessity at a mathematical level, I can leverage the asynchronous communication models. I can leverage asynchronous runtime systems to make it asynchronous across the solver, right? So what we can do is a co-design that will result in an asynchronous computing method. So now I'll briefly talk about the asynchronous computing method. So earlier I've talked about finite difference. I'll quickly recap. So what we have is a simple 1D heat equation, and this heat equation is discretized to an algebraic equation using some numerical method like finite difference. Once we have the algebraic equation, we discretize the domain, and then we compute this equation at each grid point and evolve the solution in space as well as time. In parallel, we divide the domain in this particular case into two different processing elements. Now what happens is at the edges of these boundaries, you need data from the neighboring processing element. For that, we construct this buffer and communicate those values over the network. In this particular case, you can use MPI send receive, MPI I send I receive, or MPI put, MPI get. And once the communication is finished, then only we proceed with the computation of the function at this particular grid point, right? This is where synchronization is occurring. So now what we want to do in the asynchronous computing method is we will communicate, but we will not enforce synchronization. What will happen?
You're trying to do local steps at each of those target points, right?
Yeah.
And they won't converge.
Yeah, they will not converge. They will not converge. But even before that, what happens to the time step? Will the function here at the buffer point, will it be at the latest time level?
No, because there's no synchronization.
Yeah, because we will not enforce synchronization. If the network communication is really fast, then we may have the current value. If the communication is slow, then we will have a delay in the value of the function. The delay can be one time level delay, two time level delay, or an arbitrary delay. So in general, and we do not know that value a priori, right? Because the arrival of messages at this interface is random in nature. The communication here will result in a time step which is stochastic in nature. So now here what we say is the function is at a value called n tilde. So it's not at n, it is at n tilde, where n tilde can be n, n minus 1, n minus 2, depending on how fast the communication is occurring between two different processing elements. Is that clear? So what will this do to our finite difference equation? So earlier we had all the function values that are in the black color at a time level n. Now what this particular implementation where we relax synchronization will result in is the equation here. So this is the unknown. All these are the current values, which are the values either gray or black points. The one at the buffer point, which is this I minus 1, is now at a time level n tilde, which is what you see here. So as he pointed out, this can result in poor convergence or inaccurate solutions. And we do not know what the numerical properties are. So instead of putting some value 2, 1 here, I put question marks here because we do not know what will happen if we do it that way. So to summarize this asynchronous computing concept, what we do is we have all these black points where the computations are done in a synchronous manner. That means all the function values are at time level n for these computations. This is because the values for computation at these points do not depend on communication, right? Only at the gray points, which are near the processing element boundaries, you need values which result from communication. This is where you may experience a delayed value or an asynchronous value, and that will change the algebraic equation to the one shown here. And this has some stochastic nature because the arrival of messages is random. So what are the numerical properties of such a scheme? So earlier I have shown that the numerical properties like stability, accuracy and consistency are a function of just the number of grid points, then the CFL number, the Reynolds number and the nature of the equation. When we do the same thing asynchronously, in addition to the grid resolution, the numerical properties will now also depend on the stencil size, because the stencil size dictates how many points are being communicated across the network, and also on the number of processing elements. This will define the number of processor boundaries we have. The more number of processing boundaries, the more asynchronous computations that will occur, right? And then I cannot have infinite delay between two different processors. By that I mean, if my first processor is computing a solution at time step 10, I cannot, I am probably fine computing the solution at time step 13 or 14, but I cannot compute here at a time step 100 and have a 90 time step delay, because that will result in inaccurate solutions or the solution may become unstable, right? So we want to restrict the delay to a time level n, which from the numerical computations or from the numerical analysis is determined by the stability condition. Okay? So you cannot have infinite delay. We restrict the delay for the solution to be stable, and that value is L. And then I said that the arrival of messages is random. That means the function function time level can be n, n minus 1, n minus 2. In general, I say that the delay in the function, which can be represented as n tilde is n minus k tilde, where k is the amount of delay. If k equal to 0, you have a synchronous value because your n tilde is equal to n. If k is 1, n tilde is n minus 1, that means I have one time level delay. So what is the probability in the particular simulation? What is the probability of occurrence of a synchronous value? What is the probability of occurrence of an asynchronous value with one time level delay? What is the probability of occurrence of a asynchronous value with two time levels delay? So, right, we want to characterize the change in the distribution of the delays, which in turn depends on the communication performance. How is my MPI implementation doing? How is my hardware doing? What are the network latencies associated with these messages? What are the bandwidth associated with my messages? And what is the kind of MPI implementation? Does it use some kind of optimization processes to facilitate faster computation? All of these factors affect the error in the solution. Previously, if you take a particular problem, use the same numerical method on different machines, the result will be the same, right? The result would be the same. Now, when you do things asynchronously, because the accuracy depends on all of these system parameters, you will not get a unique solution. But what we want to do in this process is guarantee an order of accuracy of the solution. I'll show those results in a couple of minutes. So I'll take a simple example. If I say that my solution can take only two time level delays, that means I have either synchronous value where k tilde is equal to 0 or one time step delayed value where k tilde equals 1. In a simulation, if I am getting 0.6 times a synchronous value, that means the number of times I go asynchronous or with a delayed communication is 0.4 times. Is that clear? So now next what we will do is, before doing some numerical analysis, what we did is we did some blind simulations. What we have taken is we complicated the equation from 1D diffusion to 1D advection diffusion equation. So this is a linear equation. we did the discretization using forward Euler time stepping and second order central difference in space. We used an initial condition which is a combination of sine waves. Because this is a linear equation, it has a simple analytical solution, and this is the analytical solution. And we use this analytical solution to compute the error in the numerical solution. So you just take a difference between UA and U, you get the error at a particular grid point at a particular time level. And what we also do is we use some random phasing in this initial condition, mainly to avoid cases where your processor boundary coincides with a value 0, in which case the derivative may also be 0, especially for sine waves. So to avoid such situations, we use some random phasing and other things. And for this particular example, the solution is periodic. That means whatever goes out of the domain comes back into the domain. So we did that simulation. So what you plot here on the left side is my spatial axis x, that means which is the 1D domain. On the y-axis, I have the function value. Initially, I have imposed a sine wave of wave number 2. That means in my domain of this 2 pi length, I have 2 different sine waves. I have evolved the solution with the linear advection diffusion equation. The linear advection or the convection has displaced the initial sine wave to the right side. So as you see, as depicted by this arrow. And the diffusion process has dissipated the amplitude of the sine wave. So you see the reduction in the amplitude. Now what I do on the left side is I compute the error in the solution using the analytical solution. So you see that the error spatially increases with respect to time. So as the time increases, the amplitude of the error increases. So these have been done in the traditional synchronous way where you do communication synchronization. I'll do the same thing asynchronously, which is this black line here. You see that the black line coincides with the red curve. That means you hardly find any difference between the solution that is obtained in the traditional textbook fashion, where you synchronize the communication, and the asynchronous way where you allow some delay in the solution. In this particular simulation, we have used 4 processors, and we have used 2 time levels for the delay, 0 and 1. And the probability is that we have imposed is that we always get a delayed value. And on the right now, we want to look at the error. You see that there are huge peaks in this error, which are an order of magnitude more than the peaks in the red color or the synchronous solution. And these peaks occur at these dash dotted lines. These dash dotted lines are the places where you have these processor boundaries. And these are the places where you experience a delayed communication. And in these cases, you get these huge errors. And as the time increases, the error is propagating into the domain, right? It is propagating also into the interior points. So now can we compute in this fashion and get accurate solutions? So that is the question. So to understand this further, what I have done is computed the average error in the domain for different grid resolutions. So I've used, in this earlier case, I've used about 128 grid points. I've used 128, 256, 512, 1000 grid points. And I plotted the error for all these cases. Because I've used a second order accurate scheme, the error here reduces by a slope of -2. So this was done using a simulation where you have a P0 value of 1. That means you are always getting a synchronous value during the communication. That means everything is synchronous, or the textbook way of computing things. Now we introduce some amount of asynchrony into the solution where we have delayed communications. Now what you see is that as I increase my grid resolution, so that means as I move from left to the right, my error decreases. That means the solution is stable. However, instead of converging with a slope of -2, I am converging with a slope of -1. That means the solution is now no more second order accurate, it is first order accurate. That means, as he pointed out earlier, it is converging, the convergence rate of the solution has reduced, or the accuracy in this particular case has reduced from second order accuracy to first order accuracy. And with the increase in the amount of asynchrony, that means the probability of having synchronous value decreases. So in this particular case, the green is 0.6 and we decrease it to 0.3 and 0.0. What you see is that the slope remains the same because this is parallel to the line that is equal to -1 slope. What changes is the magnitude of the error. So that means with the amount of increase in asynchrony, the convergence rate does not decrease, but what changes is the increase in the accuracy of the error. So can we understand these things using some theoretical analysis? So for that, what we have done is we have developed a new framework to analyze asynchronous schemes based on statistical properties. What we have shown in one of the manuscripts that is presented here is that if the original synchronous scheme remains stable, it will continue to remain stable even when you are doing things asynchronously. The second one is that we can also show that the asynchronous computations remain consistent. The major effect that you have seen in the earlier graph is in terms of accuracy, and I'll show more results and analysis on that. To analyze any accuracy of a finite difference scheme, the simplest way to do that is using a Taylor series. So what you do is, I have my this algebraic equation, right? I use a Taylor series about point I and time level n and expand all of these terms. And then I subtract the analytical equation to get what is called the truncation error. Because I use a first order accurate forward difference, I get first order accurate term for my time derivative, and I also get a second order spatial derivative term. And this is without any delay. That means my n tilde is equal to n. When I do the same thing asynchronously with one time level delay, what I find is that in addition to these leading terms, I also get these terms that appear in this red color. And these are the terms that are responsible for the increase in the error or decrease in the order of accuracy of asynchronous solutions. If I have an arbitrary delay going from a one time level delay, the arbitrary delay appears as a prefactor. It doesn't affect the exponent of either delta t or delta x. That means it doesn't change the order of accuracy, but increases the magnitude of the error. Yes, you have a question?
Yeah. So you were talking about the errors, right?
Yes.
For asynchronous and synchronous. The error is highest in when the error is highest in synchronous, the errors tend to go down for asynchronous.
Yes.
Whereas it's the other way around when it's lower for the synchronous, right? So if
no.
you can just go back to the slide.
Here.
No, the one before.
Yes.
Yeah, here. So you can see that whenever the errors reach a peak for asynchronous, they
Yes.
tend to be lower for synchronous, right?
Yeah, they are lower for synchronous. Yeah, right.
So are you using like a combination of asynchronous and synchronous?
No, this is fully asynchronous.
Okay.
Yeah.
Then what about the points where the errors are so high for asynchronous?
They continue to go high or diffuse out depending on the nature of the truncation error. So we want to analyze that, in fact, in this particular analysis. So now these are the error at each grid point at a given time level. So now what is my average error? The average error is sum of the error at all the grid points divided by the total number of grid points. So I can split this error into two different things. One is error at interior points. Interior points is where you always have synchronous computations. And the error at the processor boundary points where the computations depend on the communication and you will have asynchrony in the solution or the communication delay. So if you do the analysis further, what you would obtain is that the error now would scale linearly with the average delay that I experience and linearly with the number of processors that I use and inversely with the number of grid points. Now I think you have heard about strong scaling in one of the earlier tutorials, right? Where you keep a particular problem size constant. That means in this relation n is constant. If n is constant, it is first order accurate. There is one more way of putting these results, which is called the weak scaling, in which case as you increase the number of processors, you also increase the size of the problem such that the number of processors per with respect to grid points remain constant. This ratio remains constant. In that particular case, the error is zeroth order accurate or you get a constant error. Is that clear? So once you have this, these are the two relations. That means the error drops from second order to first order if you do strong scaling. If you are doing weak scaling of a problem, the error goes to a constant error or zeroth order of accuracy. And we have shown all of these things in much more detail in the manuscript mentioned here. So we want to validate this theoretical framework. We want to see if this linear relation that we have arrived from theory works or not.
Suppose we are calculating pressure and we are transferring pressure value calculated at the boundary point of one node to the boundary of another node.
Yes.
There will be some change. So
Yes.
Is that stochastic in nature?
You mean change in pressure?
Yeah.
No, that is not stochastic in nature. That is governed by your well-determined algebraic equations or the partial differential equations.
Sir, as you said that using the asynchronous method, the convergence rate decreases.
Yes.
And simulation efficiency increases.
Yes.
So does the reduction in the convergence rate outnumber the increase in the computational speed?
I'll come to that in a couple of minutes. Okay. So before that, I'll quickly show you some validation of our theoretical framework. What we plot is the error in the solution with increase in grid resolution when we have used different kinds of processor number counts. So in the red line, we have used only 2 processors, and subsequently we have used 8, 32, and 128. What you see is asymptotically at the extreme, it always converges with a slope of -1, which is first order accurate, which is what we have determined from the theory. And the theory also mentions that the error scales linearly with the number of processors. So this is what so here we plot the error as a function of the number of processors, and you see that there is a linear scalability. And then we also do the error analysis in terms of weak scaling, where we keep P over N constant or N over P constant. In that particular case, we should get a constant error. So we do the numerical experiments and we find that these values plateau to a straight line. So asymptotically, this is 0th order accurate. And we get an inverse scaling law of -1, and that's what we find in our numerical experiments when compared to the theory. So we have developed, in addition to the whole computing framework, a method to analyze the error and do some predictions on the kind of error that we are getting, right? So even if you take so until now we have taken only second order accurate schemes. So now we go to higher order of accuracy, we go to 4th order. And you see that even if you take a 4th order scheme, the accuracy doesn't drop to 3 or 2, but it drops to 1. And the same scaling relation for the error works. So can we do accurate simulations with these kind of schemes? Yes or no? We cannot, right? So we cannot use these kind of inaccurate schemes for high fidelity direct numerical simulations. So for that, what we have come up with is, can we come up with asynchrony tolerant schemes? The numerical schemes which can perform computations asynchronously but maintain the same level of accuracy as synchronous schemes. For that, what we have to do is, if you remember earlier, you had in the truncation error those red color terms. Those terms have to be removed from the truncation error. And how we can do that? We can do that by changing the stencil. So let me take a simple example. If you use a 4th order accurate scheme as shown in the previous slide, it uses a 5-point stencil. That means to compute the solution at point I need values from I minus 2 to I plus 2. If you do the things synchronously, it results in poor scalability. So what we do is we do things asynchronously, where you have delayed values on the right side, which are the buffer values coming from the neighboring processor. So this will result in poor accuracy, but increased scalability. So now to reduce the error, what we do is we expand the stencil size, which can be done in 2 different ways. One way is we add one more point on the either sides. So we make it from a 5-point stencil in space to a 7-point stencil in space. So what is the effect on HPC machine with increasing stencil size? This will result in, at the first order, larger message sizes. So previously you are communicating only 2 points. Now we are communicating the values from 3 different points. So the message sizes have increased. The other way is you can also increase the stencil size in time. So at these points I plus 1 and I plus 2, in addition to the values at n minus k, I can also take the values at n minus k minus 1. So the leading order effect here is that this is still a 7-point stencil, but I expand the stencil in time, and this will result in increased memory requirement per processing element. So that means you need a larger memory allocation per processing element. So with these kind of things, considerations, we have developed what are called these asynchrony tolerant schemes. A simple example is given here, and this looks very long, but all these are very local computations, and these schemes are applied only at the processor boundaries. Everywhere else in the interior of the domain, things are done using traditional textbook synchronous schemes. We do the simulations, repeat the same things as before. You have seen that here you have this huge gap. And we do the same things with asynchrony tolerant schemes. Everything falls on top of each other. Now, what is the advantage? We are getting an accurate solution comparable to the traditional textbook way of computing things. And now we are doing things asynchronously. That means we gain a lot in terms of reducing the communication time. Right? And for this, we have a scalability law that comes in this form. I will not go into the details here. But if you are interested, you can read up this paper, which has a detailed analysis. So these were all for simple 1D linear equations. What about nonlinear equations? So we have performed simulations for those as well, and they also maintain accurate solutions, which I will not go into the details. So now that we have looked at the mathematical aspects of asynchronous computing, which show that the error will not just depend on the numerical parameters, but they will also depend on system parameters when you do things asynchronously. Now, what about the implementation? So, for implementation, I would like to point out to a simple example of an asynchrony tolerant scheme. What you see is that some of the coefficients in the scheme, so here the coefficient is 1 for I plus 3, the coefficient is minus 2 here for I plus 2, and so on. For some of them, the coefficient is a function of the amount of delay that I am experiencing, right? Which is in terms of k plus 1 in this second line, and in terms of k tilde in the third line. So that means you need to know if I am getting a delayed value, how many time steps is it in terms of the number of, how delayed is it in terms of the number of time steps. I need to know that to recover the accuracy of the solution. And second thing is that the communications have to be asynchronous. That means you cannot use the typical MPI send receive because they are blocking communications. You have to use asynchronous communications, which are something like MPI I send and I receive. And in MPI I send and I receive, the synchronization call is MPI wait. Wait is when it will finish the communication process. We will not post it because we want to go things asynchronously. So you do the synchronization or do an MPI wait post only if the delay is more than the allowable delay in the simulation. Is that clear? So once you have that, and then the next thing is that we have function values at different time levels, right? I have values from n minus k tilde, n minus k tilde minus 1 at two different time levels, as I showed in the earlier picture. And then the fourth thing that is important is atomicity. How many of you know what is atomicity in accessing data values? Yeah. So what is it? Right, that's right. So quickly let me explain using a simple picture. So let's say I'm trying to put a value from here to here, and what this processor can do is simultaneously it can use this value to do the computation at its neighboring point, right? So this processor is trying to change the bits in this memory location, and this processor is trying to access those bits to do the computations with respect to the neighboring point. If both the things are happening simultaneously, you may end up with garbage. That means while this is modifying some of the bits, this takes those partially modified bits to do the computations, which result in junk values, right? So that is not allowed. So either in the asynchronous case, either you have an older value completely or the newer value completely. You cannot have arbitrary changed bits or partially changed bits. So that's what is important when you do things asynchronously. So these are the four different requirements. So with these requirements, how do you design an implementation? So that is the question. So let's do it the traditional way. So the traditional way is just I take MPI I send and I receive. I can use MPI tags for the timestamp to compute what is my k. So if I want to send a value from here to these two different time levels, these are the two buffer points. So let's say a time n minus 2, I have sent it to the bottom level, and at n minus 1, I have sent it to the top level. Now, where will I send the value of n? I can either send it to one of these. But again, atomicity is important, and then the memory access is very important, right? So in that particular case, I have to do some memory management of where am I having the latest time level, and that becomes complicated. So, and then if you use latest interconnects, what happens is if you send messages sequentially, they can appear at the destination not in the same order, but in a different order, because different message packets can take different routing routes on the network. So that results in messages out of order. So in these particular cases, the management of the timestamp associated with the data becomes very difficult. So for that, what we do is we will not send the values from S directly to the B. Instead, what you do is we create a buffer array, which is of the size of, which is of the length or the height equal to L. L is the amount of allowable delay in the simulation. So what we do is, here we in the receive buffer, in the source processor we post the MPI I receive. In the destination processor we post MPI I receive. In the source processor we post MPI I send. We will not post any weight, and we start sending values. So the n minus 2 value is sent to the third level, n minus 1 is sent to the second, n is sent to the first level, n plus 1 will be sent to the lowest level, and so on. So this buffer operates like a ring. And if all the values are not updated in this ring, then you post a synchronization call, which is the MPI wait. If not, you go things asynchronously. So now to compute the solution at this point I need the buffer values. So I'll check what is the status of communication using MPI test. If I post an MPI test with a particular tag, it will check whether the communication associated with that particular tag has finished or not. So with that, I can say that in this particular case, the communication at n minus 2 and n minus 1 has, let's say, has finished. N is not yet finished. Then I take the values from n minus 1 and n minus 2 to this buffer and then do the computations. Is that clear? So if n is finished, then I take the n. Instead, if not, I just take the older values. If n minus 1 is not finished, I take n minus 2 and n minus 3, and so on. And then I get the timestamp value, which is these box values, using MPI tag. So I put the tag equal to the timestamp value. So this is using the two-sided communications, non-blocking way. I can also do this thing using MPI one-sided communications. So what you have to do in this particular case, as I mentioned earlier, you expose this receive buffer as a remote memory. And once you expose this as a remote memory using MPI win, so which is called a window, what you do is now you start using MPI put to do the communication. Now the destination processor is not involved in the communication at all. Only the source processor is involved in the communication. And unlike two-sided communications, we do not have a mechanism to tag these communications. The MPI standard does not support any tagging for one-sided communications. And without the tagging, we do not know what the timestamp values are. And unlike the two-sided communications, where you have a function like MPI test or MPI probe to check the status of the communication, whether it's finished or not, here we do not have a MPI test function for one-sided communications. But we need to know whether the communication is finished or not, right? Then how do you obtain that? Any thoughts? So now you are sending the values. You do not impose any synchronization to ensure the communication is finished. But I have several levels of communication that are happening. How do I know which ones are finished?
Since you're talking about a queue-like structure,
Yeah.
You know that task 0 is going to take the first 3 values or the first 4 values,
Okay.
and so on. So everyone will take every one of those processes in the subtask in task 0 will continue taking values.
Right. But these things happen over and over again, right? Yeah, because these are time-dependent simulations where you evolve the solution in time. These things reoccur. Like so, this buffer is like a ring.
Yeah.
As you increase time.
Yeah.
So what we have come up with is that we create one more buffer, which is called the be changed to check whether something has changed or not. So what we do is initially, we initialize the values of the function to be equal in both the buffers. And whenever I receive a new communication, there will be change in the value, right? And then, so what I do at each time step is compare these two arrays at each time step. And doing a comparison, if it is equal to, if the values in the change and the receive buffer are the same, then the communication has not yet finished. If the values have changed, then something has happened. Some communication has happened. So if the values are unequal, then we have a communication update. That's how I know it. And then I use those values to do the computation, those latest values. However, this fails. When does it fail? If the values of the function do not change with time, right? So to address that issue, what we have come up with is, instead of doing initializing these values to be equal, you can use the sum of the values. So the value here is equal to the older value plus the sum of the current value. So in that particular case, you have an addition where even if you are receiving the same value, it becomes double, and then you can change the, you can know the status of the communication. Still it fails in one particular case, when the value is equal to 0, because 0 plus 0 is still 0. So one of the...
Would it be better if you take the receive buffer, you don't use an alternate buffer, and you periodically flush a few values, and you add an error? So,
but flush is like a synchronization call. We don't want to synchronize, right?
Yeah.
So flush is like a synchronization call. You don't want to synchronize. So we want to go fully asynchronous. So we need to come up with some local algorithm. So finally, what I thought the best thing would be is to add a small random number to the value at the source and send the function value added with the random number. The random number seed in both these locations is the same, so that the sequence of numbers that I get is the same, and that can be used to check the status of the communication. So in this, just to summarize this, what you do is you expose the buffer as a window, as a remote memory. You use MPI one-sided communication, MPI put, to send the values. You check the status by comparing it with the change buffer, and then update the communication status at different levels. So with this communication model, we can finally design an asynchronous algorithm which has 3 components. One is the initialization phase, where you provide the initial conditions to the function and so on. And then you run the first few time steps, which is equal to the L number of time steps, in a synchronous fashion. This is just to populate the buffer. And once you have populated the buffer, you index the buffer to get the timestamps. And once you have done the indexing, you go fully asynchronous, unless the delay between the 2 different processors is greater than the value of L. Here what we are doing is, if you go from A to E, you compute the solution at the interior points where the computation is independent of communication. You check the status of the communication. If the synchronization is required, you synchronize. If not, you proceed asynchronously by updating the values at the processor boundaries. And then you initiate the communication for the next time step. So this is how the algorithm works. Now we want to look at briefly the performance results. So are we going to really save doing all these additional computations? This is the question, right? So what we can do is we can measure the performance in 2 different numbers. One is we can do strong and weak scaling. The other is we can look at the distribution of the amount of delay. If the delay is lower, that means you get a faster performance. And we have used both 1D and 2D, 3D simulations to benchmark the computational method. And the simulation parameters are chosen very close to the practical applications. So here I show the distribution of delay, K tilde, measured at different processing element boundaries from an actual simulation. So in this particular simulation, I've used 128 grid points. I've used 8 processing elements, and I've allowed a delay, maximum delay of 20 time levels. So if there are 2 different processors, one is running really fast, that means it will get a delayed value from the neighboring processor, but the delayed processor will get values from the future. Do you see that? So there are 2 different processors. One is running really fast. In this particular case, let's say this is running at time step 20. This is running at time step 10. The one that is running at 20 will start sending the values from 15, 16, 17 and 18 to the one that is running at 10. So it is very likely that the processor that is computing that at a 10th time step will get values from the future. So that's why you get a nearly symmetric distribution across the mean, right? And here you see that all the processors hit a maximum, have some significant values at L equals 20. That means there is some synchronization that is happening if you use this kind of MPI implementation. So what we get in this particular simulation is a mean delay of 10 time levels, and the standard deviation is 6 time levels for the delay distribution. We have used a one-sided communication model from our collaborators at ETH Zurich. What that has done is reduce the mean delay to 1 time level. That means we are getting a better MPI performance from their implementation, and the standard deviation also reduced to 2. That means you compare the solution from both these simulations, you will find that the one that we get from a lower mean value will be more accurate, right? And what does this do in terms of strong scaling? So I come back to the strong scaling graph. Here we plot the number of processing elements on the x-axis. We measure the time taken to do one time step computation. For this particular process, for this particular experiment, we have used Burger's equations, and we have used 32K grid points. We have used a delay level of 20 time levels. If you do the traditional way, which are these red dots in a synchronous fashion, things deviate from the ideal scaling line. We do the same things asynchronously with asynchrony tolerant schemes. Now we are able to maintain linear scalability. So you do not have this communication overhead. And why did this happen? Because if you look at the PDF, we have never hit a delay of 20 time levels. That means we never synchronized. We are always doing computations asynchronously. And that improved the scalability. And this is for a simple 1D problem. What about a more realistic 3D problem, which uses a larger number of grid points? So here the number of grid points is up to 120 cube. So these are about 1 million grid points. And we have used up to 12,000 processors to do this simulation. And you see that as we increase the number of processors or the computing nodes, the execution time for computation reduces. This is what we get, right? The linear scalability line. So it reduces. The communication time remains nearly constant. And let me clarify here. The left graph is for traditional way of computing, which is a synchronous way of computing things. The right graph is for asynchronous way of computing things. So here you see that after a certain amount of increase in number of nodes, the communication time overwhelms the computing time. So that affects the scalability of the codes. However, when you do the same thing asynchronously, your communication time significantly reduces, and you are able to maintain nearly linear scalability. Your scaling mainly is dominated by the computation time, not by the communication time. And so one can ask, what are these error bars? We have repeated each of these experiments 20 times because there is performance variability, right? We see that the performance variability in communication has large error bars when you do it in a synchronous fashion. However, when you do it asynchronously, the error bars have almost disappeared or reduced. So that means asynchronous way of computing things can also handle or address the performance variability of supercomputers. So we do the same thing. So finally, we want to see what is the final scalability. We have used both two-sided and one-sided communications. For the synchronous way, which are the light color purple and dark color purple lines, things deviate from ideal scaling. Here we try to maintain near ideal scaling for asynchronous case. So at the extreme scale, when you use 1024 MPI ranks, we get about 2x speedup. And this gap would further widen when you go to extreme scale, about 1 million processors. So we also looked at things in terms of weak scaling. In weak scaling, if ideally, the line should remain a flat line because as you increase the number of processors and the number of grid points, the workload remains constant. So it should be straight. But the traditional synchronous ones deviate and move away from the flat line. However, the asynchronous ones remain nearly flat. So here also we experience a maximum speed up of about 2.2x. So finally, I'll not go into the other research highlights, just to show here we do a direct numerical simulation of a gas turbine combustor. A gas turbine combustor here in this particular case is used for power generation. And in this simulation, we use about 1.25 billion grid points, and we simulated this on 50,000 processors. And we are also looking at aerospace applications. We are looking at simulation of scramjet engines for hypersonic flight. And here in this particular simulation, we use about 2 billion grid points and 200,000 processors. So that's the scale. This is the extreme scale at which we want to do the simulations and understand that detailed physics. And also we are looking at doing some integration of ML and AI into our simulation workflows to reduce the data footprint and to do a better data management. So finally, I'll conclude the talk by giving you the final conclusions. We have provided a basic overview of how to solve a PDE using finite difference method. We looked at the parallel implementation. Then to improve the scalability, we looked at asynchronous computing method. We have developed a theoretical framework to understand the error and validated that error with some numerical examples. We have devised an efficient algorithm to do the asynchronous implementation, and we have shown the scalability. And these things show a promise as we move towards exascale. In terms of our future work, we are looking at doing this DNS in an asynchronous way for 3D reacting flows. And we also want to couple them with asynchronous runtime models to get the full advantage of asynchrony across the stack. With this, I would end my talk and would like to take some questions. Thank you.
Sir, if we compare the results of the simulation like pressure contours, velocity contours, do they match in both the cases?
So they will not exactly match, but the error between the two will be within the order of accuracy. So they will not be exactly the same. Even if you run the same asynchronous simulation twice or thrice, the answer would vary a little bit, but the variation is within the order of accuracy.
Suppose if we do simulation or a flower
Right.
circular cylinder, then the frequency of the vibrations,
Right.
do they match?
So let me answer this in a different way. So let's say you do the simulation in a synchronous fashion. There's no asynchrony involved. You do the simulation with a second order accurate scheme and fourth order accurate scheme. What happens? Will the frequency of oscillation remain the same? It will remain nearly the same if you use sufficiently enough grid resolution, right? That is the grid convergence. So the same thing is applicable when you compare the synchronous solution with the asynchronous solution. So if you are sufficiently resolved, the error that is induced by asynchrony is insignificant and will not affect the solution. If there are no further questions, I'll take leave for today. Thank you.